Good morning, everyone. So today we will be discussing about the development of X-band low-level RF prototype for the Praxia Spark Lab Linac at INF and Frascati. Uh, Moving on with the outline of the talk, I will present a little bit of brief introduction about the Praxia project and the doctoral network, and then give some introduction to the low-level RF, and then about the current S-band Libera LLRF. And moving to the motivation, it's about the X-band and its challenges, and moving on with some preliminary results and the future outlook. So the Praxia project, the Praxia stands for European Plasma Research Accelerator with Excellence in Applications. And it's an innovative electron accelerator. It's like laser and electron-driven wake field accelerator. The main advantage of this accelerator, it's we can achieve high performance, compact in size, let's say a few hundreds of meters, and then it's cost efficient. And it has various number of applications where it can be used for medical imaging and high energy physics research, and for industrial applications as well. Here is the image of how wake field acceleration looks like. Here it's the drive particle, the laser that generates the wakes, and you want to insert the witness particle here so that it sees the acceleration and it feels it. So moving on to the doctoral network, I'm a part of this Praxia doctoral network. It comes under the Marie Curie actions with an allocated budget of 3.2 million euros. So there are like 12 high-level fellowships within this doctoral network, where 10 will be funded by the European Union, and the other 2 by the UKRI guaranteed funds. So the main aim of this doctoral network is to perform interdisciplinary and the cross-sector plasma accelerator research, and then the training is being carried out between the universities, industries, and the research centers as well. And also, the network has recognized importance of the research at R&D at a European level. And here are the 8 beneficiaries that are part of the doctoral network, including the ITEC, and then the 15 other associated partners here. Moving on, now it's the introduction to the low-level RF. And what you see in the image is the structure of how a LLRF is. It's a subsystem for the radio frequency for the RF system, and here you see the RF cavity. Okay, and then we have the probe signal coming into the LLRF instruments, and where it's like compared with the reference signal, and then if there is like a deviation between the reference signal or the probe signal, then the feedback loop gets activated, and then it corrects it to stay within the reference signal. And here, and then the signal is the drive signal, and it was sent to the pulse modulator plus klystron. Here is the example of a power amplifier, and then through the waveguide again to the cavity. So here we have also a benefit of user-defined set point values, where you can adjust the amplitude and phase in real time. So moving on, I would like to give some insights about the current Libera LLRF system. On the right is the analog front end. On the left is the digital processing unit. And here you have the input RF signals that goes into the analog front end that generates the IF frequency input signals, which goes into the ADCs, and then through the FPGA, the fast links, and then we process them here in the digital processor unit, and then again converting them from digital to analog and to the back end, and finally generating our drive signal. So here are the 2 instruments, like for the LLRF, how they look like. And here are some of the differences, like the customers that use the Libera LLRF now, for example, Eli MP Vega, the STFC, Clara, INFN, and etc., and other projects. Moving on, the motivation of today's topic, it's about the X-band low-level RF frequency. And the main aim of going to the X-band is to move to the higher frequencies, which allows us to achieve higher accelerating gradients and making the structures more compact. The main challenge of the X-band is to control the RF parameters such as the amplitude and phase at these higher frequencies, and that too for very short pulses. And apart from this challenge, we also have the other thing, it's about the temperature drifts at these higher frequencies. As of now, there is no commercial LLRF instrument that is working at this X-band, and also that meets the requirements of the Praxia Spark Lab LINAC. And here are a few preliminary requirements of Praxia X-band, and they are still under discussion from time to time. And the highlighted ones are just for your insights, where the carrier frequency is at 11.994 gigahertz, and the sampling rate here it's 250 megasamples per second. And then the phase jitter, or then the vector modulator jitter, it stays like less than 0.01 degree RMS. And just it's for a prototype, the number of RF input channels is 2 and the output is 1. So here in this slide, we will, I will be showing about the research activities that will be carried out to develop this prototype. The first one would be to define the X-band LLRF concepts, like to understand it, and then to select optimal components, which one, like performing individual tests on the components, and then joining them block by block and designing one or more prototypes. And finally, validating them at ITech, and then verification, performing the laboratory tests at INFN as well. And once confirmed on the test bench, this prototype will be used as the starting point and will be industrialized into a commercial instrument as well. So moving on to the main diagram, I think this was the one that Manuel showed in his introduction slide. This is the basic conceptual block diagram of how a X-band LLRF prototype looks like, which I was working on. So here you have two blocks here. This is the front end, analog front end, and the digital part here. The main aim of this, the block diagram, we use a single stage down conversion, which is here, which we convert it into the IF frequencies that we send it to the ADCs module, and then the double stage conversion here, where we generate the drive signal. So moving on, currently I'm working with a part of this prototype. I could share these results with you now in a moment. So it's the LO and ADC synthesis block. These are the local oscillator and the ADC signals, the generation of these signals, how we are generating them. And on the right, it's a block diagram, but here it's the architecture tree on how we are getting the input of 12 gigahertz, and we are generating the MO itself and the sampling clock signal for the sampling clock, and the other LO signals here. So here are a few images of how the schematic looks like, and how it's connected, how it's arranged, and each individual tests were done on each of the components, and also we tested them by connecting them in a chain and performing them block by block, and now also doing it on a whole. So these are different types of tests that we done using the spectrum analyzer and the network analyzer and the signal source analyzer as well. For example, if you can see here, there was a low pass filter. We need it for working frequencies of 3 gigahertz, 400 megahertz, and 250 and 80. And here are the tests that were done. For example, the S parameters and also the frequency response for S21 versus frequency. And the same for the amplifier as well. So this is how the measurement setup looks like in the lab at ITech. And for example, like here we have the stack of the spectrum analyzer and 2 of the signal generators, and measuring just the output of the block. And to see it, like the 2 blocks were combined, where the drive goes here and then we get the outputs here. It's not like a snake, but I feel like it's a space station, International Space Station. And then we have the outputs here, everything. It looks messy, but once we fit them in the chassis, it would be like really beautiful. And this is the output or at one of the port there at the output port. That's from the signal analyzer. And the results that we are getting until now, they are like expected. And then I could say they are even more like better results. So this is another topic about the phase noise measurements, which I have recently started them. We have a new SSA in the house that can go up to 26 gigahertz. And here, this is just for the brief understanding of the input versus output phase noise of an amplifier, where in the blue curve, you see the input that's directly from the signal generator to the signal source analyzer. And then in the black, you see the after the amplifier. It's basically after the amplifier. What you see here, there is not much difference, or we could say there is no much contribution from the amplifier with this phase noise. Here, another interesting topic within this prototype, it's the development of good cavity filter. Here is an example of a cavity filter that works at the frequency range of 3 gigahertz, that has a ceramic resonator in it. Here you can see the Teflon screws here. I will explain it later, which are used for tuning. And with this, what we can achieve is like we can tune this cavity with the help of this resonator, and then we can achieve the frequencies of our interest. For example, like around 3 gig plus the IF frequency that we are using now. And here is the response curve of the filter that has a good insertion loss. And then moving on better, now we were also planning to, for the time being, we are using this, but in future, we are going to use a small cavity filters, putting them in cascade. So for space requirements, everything. And finally, going on to the outlook and conclusions part. This is the diagram, another diagram that Manuel showed you before. And we are planning now to put everything fit in this chassis, and then to do the performance tests using the signal source analyzer, etc. So that's how the chassis now it looks like. And concluding it, I have a list of future tasks that will be performed in the coming days. First thing will be the assembly of components into the 19-inch chassis, which will be done by the end of this month. And then we start doing the performance tests of the front end. That's a part of prototype. And then and parallelly doing the evaluation of the back end. That's planned for the end of summer. So, and finally, we were planning to finalize the prototype by the end of this year, December, and then perform the laboratory tests at INFN, the text facility, at the early 2025. Thank you, and have a nice Libera workshop. If you have any questions, I'm happy to take.
Do we have any questions?
Yep.
So you mentioned that temperature drifts
Yep.
have big influence on the system. So have you noticed that?
Not as of now, just we are now assembling them. But the prototype doesn't require the temperature stabilized, but maybe the final instrument, when we commercialize it, then we have to do it the temperature. The Praxia, like the INFN, gave us these requirements. They mentioned that they don't need it to be temperature stabilized.
The prototype would be difficult to have it temperature stabilized because it would require a lot of work.
The cost increase for the prototype as well.
But I mean, at least in the X-band systems, and we plan to use the same approach for the X-band, we would like to have all the RF part into a temperature stabilized grid. I think that comes from long-term requirements we've got from projects. And yeah, that's the idea. I think that was also the question from Phani to you before. If you noticed any
Yep.
Yes,
effect of temperature.
Yeah. That's something we can discuss later.
Yeah, we can discuss it later. Yeah.
Okay.
Yep.
So for your prototype, you've used these connectorized components.
Yep.
and you want to now integrate them into a box.
Mm-hmm.
Later for production, is your plan also to stay these connectorized components, or do you want to integrate it onto a PCB?
No, we integrate it onto a PCB.
Okay.
Like we are also doing it parallelly now.
And that, if my estimation is right, is the first time that such high frequencies are involved in any project inside instrumentation technologies, or is there pre-existent?
No,
experience
it's from scratch. I could say it's from scratch.
Okay.
Yeah, we are doing it from
Are
scratch.
you expecting any issues?
Maybe like not as of now, but one thing could be the long term. I hope so, but it could be corrected as well
Okay.
with the tests that we are doing now.